pendulum consists of a uniform disc with radius 0.1 meters and mass 0.5 kilograms attached to the end, like a lollipop, of a uniform rod with length 0.5 meters and mass 270 grams. Total length from pivot to end of the disc is 0.7 meters. All right, let's visualize this. Drawing is good. A long rod. Start with that. A uniform rod with length of 0.5 meters and a mass of 270 grams, and a uniform disc with radius of 0.1 meters and some mass. And the total length from the pivot to the end of the disc is 0.7 meters. So if the disc has a radius of 0.1 meters and the rod to the end is 0.7 meters, that means the disc is attached at its edge to the rod. So got 0.1 meters there. All right. Thankfully, we've got this problem broken down for us so we don't have to figure out all the parts. First, calculate the rotational inertia of the pendulum about the pivot. All right, so the pivot is here, and we've got essentially a compound object. We've got a rod and a disc and a disc. So let's figure out the moment of inertia of each of them and then add them together. The moment of inertia total will be the moment of inertia of the rod plus the moment of inertia of the disc. So the moment of inertia of the rod, it's rotated around its end, so that's going to be 1/3 ml squared, the length of the rod, plus the moment of inertia of the disc. That's going to take a little bit of consideration because the disc is not rotating around its own center. And so because the disc is rotating, certainly as it goes around, as it oscillates, the disc is going to undergo some rotation, but it's not rotating around its center. It's not even rotating around its edge. It's rotating around a point well far away from the edge. And so we need to determine the moment of inertia using the parallel axis theorem. So the disk is going to be its original moment of inertia, as if it was just rotating around its center, plus md squared. So what's a disk around its center? That's 1/2 mr squared plus that mass again times d squared. And the radius is 0.1 and the distance all the way out to the end of the rod is 0.5. So the d is 0.6 meters. This disk is rotating at a point 0.6 meters away from its own center. So the total moment of inertia is going to be 1/3 the mass of the rod, which is 0.27 kilograms, times the length of the rod, which is 0.5, plus 1/2 of the mass of the disc, which is 0.5 times r, which is 0.1 squared, plus, again, the mass of the disc, which is 0.5 times d, which is 0.6 squared. So the total moment of inertia is all that.
The next day.
0.205. Great. Whew. All right. Wonderful. Number crunching is hard. All right, so we've got the moment of inertia of this compound object. Great. Now, we need to determine the distance between the pivot and the center of mass of the pendulum. All right, let's find the center of mass. I'm going to treat this as though it's on its side at the moment, just so I can use x. So the x center of mass is x1 at its, m1 at its location plus m2 at its location over the total mass, m1 plus m2. So if we continue to treat this as two separate objects, the rod and the disk, we can say that the mass of the rod exists at its own center of mass, which is going to be halfway down the length of the rod, which would be at 0.25 meters. And the center of the mass of the disk, again, if we're calling this position 0, then the center of mass of the disk is going to be way out here at 0.6 meters. So the mass of the stick is 0.27 times its location, which is at 0.25, plus the mass of the disk, which is 0.5 kilograms at a location of 0.6 meters, and the total mass is 0.27 plus 0.5, the stick, the rod plus the disk. So the center of mass of these is going to be located there.
16 paranoia-filled days later.
0.477 meters. That worked out nicely. And now let's find out the period of oscillation. All right, so we go back to that period for a physical pendulum. Period for a physical pendulum is 2 pi root I over mgh, again, where h is not the height that it falls, but h is the axis to center of mass distance, which we just found. This is h. So now we can just plug these values in. We get 2 pi times the square root of 0.205 over mass, total mass, which is 0.27 plus 0.5 times g, which is 10, times h, which is 0.477. 2 pi times all that stuff.
Moments later. More moments later.
Works out. Time is 1.48 seconds. All that stuff in there. Yeah, that is not an enjoyable process. In fact, 2/3 of the questions are not overly onerous. Finding the center of mass, not terrible. Using a formula, using values you already have, not terrible. Really, the terrible part goes all the way back to rotation, where we had to deal with not only a compound object, but also one where we had to involve the parallel axis theorem.